So this chapter is probably one of the more difficult chapters in this unit, but I'll start off easy and we'll get to these fusion-fission sections. Okay, just as a review, this is an example of an atom from the periodic table, an element. And this top left-hand corner, again, is the atomic number. And then this bottom one is the mass. Here's another way that we write this, and you'll see this more in this chapter. This top number is the mass number, and that's protons plus neutrons. So as you see, helium has 4, so it has 2 protons and 2 neutrons. And then the atomic number is just protons, so 2 for helium. Okay, so that's the basics. Now this is the graph that you need to understand. So first of all, a nucleon, or for the average nucleon mass, nucleons are just protons or neutrons. So a proton is a nucleon, and a neutron is a nucleon. So this is saying, this is showing basically the periodic table strung out in a long line. So this is hydrogen, helium, carbon would be in here. So this line is basically made up of all the points of all the elements. And so this graph is showing that as you get down the periodic table, the nucleons, or the protons and neutrons, start weighing less. We'll see this in this example. So here's a fusion example, and we have hydrogen and hydrogen, which is represented right here on this graph. So when 2 hydrogens come together, notice they have 1 proton and 1 neutron each. But when we fuse them together, we get helium, and the protons and the neutrons get smaller. They actually decrease in size here. There's a total same number, so there's 4 here and 4 here, but the 4 weigh just a little bit less. And our friend Einstein figured this out in the E=mc² equation. So when mass decreases, energy also decreases. So helium gives off energy. So when we do a fusion reaction and the mass gets smaller, the average nucleon mass gets smaller, then we get energy out of it. And that's fusion. So if we went from hydrogen down to helium, this gap represents the amount of energy that we gained from decreasing the nucleon mass. Okay, now if we were to combine, let's say this element, then we get an element higher up with a higher average nucleon mass. And so if we did that, then mass would increase and energy would also increase. So that reaction would require energy, and it would take in energy. So on this side of the graph, we don't combine, we break in order to go from uranium down to, let's say, xenon or strontium. I believe those are the element names. So if we go down this graph, then the average nucleon mass would decrease. And if the average nucleon mass decreases, then the energy will decrease and the reaction will give off energy, which is what we harness. So this was a fusion example from this left side of the graph. And then we have this fission example where we break apart a big atom. Uranium happens to be the biggest naturally occurring element. And so this is the example that we give. You don't have to know the examples, but this is the concept. So we just give uranium a neutron. When uranium gets one more neutron, it's too much mass for uranium to handle. So it goes, whoa, this is too crazy. I'm going to break apart. And so we go to xenon and strontium. We go down this graph, decreasing the average nucleon mass, thus decreasing energy, and so it, again, gives off energy. And then these neutrons will go on and break apart other uranium atoms. And that's the chain reaction of fission. Now, in fission, This is what we use in our normal reactors to get energy. Fusion we can do, but it just requires so much energy to control the reaction that we don't get any energy out of it. So it's not really feasible for us to do at this point. Now, those are fusion and fission and the graph. Now we'll go to radioactive decay. So fusion and fission is what we do to atoms in order to get energy out of it. Radioactive decay is something that happens more naturally. So there's 3 examples: alpha decay, beta decay, and gamma decay. Now the thing you need to know about alpha decay is that it loses a helium atom without the electrons. So it loses a mass number of 4 and it loses an atomic number of 2. And so here's an example. What you need to be able to recognize is an example and then identify the type of decay. So if you saw right here that this reaction gave off a helium atom, then you'd know that it was alpha decay. Beta decay is a little bit more complicated. With beta decay, the atomic number increases by 1, and 1 electron is lost. So this bottom number, see here, it goes from 6 to 7, but the mass number doesn't change. So ultimately, that means that the way we think about it is that this neutron turns into a proton and it emits an electron. So you see here, this is a total number of nucleons is 14, so carbon 14, but there's 6 protons. And in nitrogen 14, it has a total number of nucleons of 14, but as you see here, this neutron, we think of it as partly proton and partly electron. The electron gets emitted, and then that neutron turns into a proton, effectively increasing the atomic number by 1, but not increasing the mass number. Okay, that's beta decay. And then lastly, gamma decay is pretty simple. There's just no change. In this example, it goes from 222 to 222, 86 to 86. All it does is gives off this high energy gamma ray. That's what we call it. All right, and that's chapter 25.